Welcome. This is the next lecture on LTE, and this lecture deals with the protocols that are related to LTE. So LTE is more than just a wireless protocol. It does have a related system called System Architecture Evolution, or SAE. It is a companion to the LTE protocols, and it deals with how the network elements communicate with one another. And when I say network elements, I mean mostly elements that are on the wired backbone. So we're not really talking anymore about how the base stations communicate back and forth with the wireless terminals, but rather how the infrastructure elements like the base stations and gateways and things like that communicate with one another. So one of the key concepts is that the base stations themselves, the E-node Bs, have the ability to communicate with one another, and this is over what's called an X2 interface. And this is important because in the context of ICIC, or interference coordination, intercell interference coordination, the base stations have the ability to talk to one another and coordinate what frequencies they use, let each neighboring base station know what frequencies are congested and which ones are available. And that's all done over the X2 interface. And then in addition to the base stations communicating with each other, they need to be able to get their data out to the outside world, to the internet. And that's done by communicating over a so-called S1 interface out to a gateway, or a serving gateway here. Here's a serving gateway. In addition, within the network infrastructure, you have to keep track of roaming, who's authorized to be in your cell, and that's all done with a so-called MME, or Mobility Management Entity. So an MME keeps track through a home location register and a visitor location register of who should be in the cell and who is a visitor to the cell. So LTE in general uses a layered architecture, and at the lowest level you have a physical layer, and here we have the UE, that's your mobile unit and mobile terminal, and E-node B, that's your base station, and they can communicate through a peer-to-peer connection at the physical layer. Going up layers is very much like the OSI layered protocol stack, although it's a little bit different. You have a MAC layer, medium access control, you have RLC, or radio link control, you have a packet data convergence protocol, PDC, and RRC, which is your radio resource control. And then finally there's this non-access stratum, which is used, it actually bypasses the E-node B, but this is how the UE is able to communicate directly to the MME, or Mobility Management Entity. Here's another look at the protocol architecture, and you have an E-node B over on the left. The right is a UE, and you can see down here at the low level you have the physical layer. What's going on inside the physical layer includes you have some coding, that's your air control coding and modulation, antenna resource mapping, and you have the complementary procedure on the other side of the channel. And then if you were to go up one level, you have at the MAC level, there's a multiplexing or demultiplexing. The hybrid ARQ is handled at the MAC layer. And then if you go up one layer above that, you have radio link control. This is where a higher layer automatic repeat request protocol is used. Now over on the E-node B side, you have the scheduler. And we saw in our last lecture, scheduling involves determining what frequencies are being used at any given instance of time. And so the scheduler is a very important part of the base station. Looking above the RLC layer, you have the so-called PDCP, or Packet Data Convergence Protocol, that deals with ciphering and header compression. And this is yet another view of the radio protocol. So again, you have the physical layer at the lowest layer, you have a MAC layer. MAC layer handles one or more hybrid ARQ sessions, and then above that you have some RLC sessions, and you have some PDCP sessions. you have one RRC session, and you have the user applications. So let's talk about some of the layers in a little bit more detail. Top-down PDCP I mentioned is the packet data convergence protocol layer, and it's really doing two things. I suppose it could have been split into two sublayers, but one of the things it does is header compression. So think about if you're doing something like voice over IP. Those are pretty small packets, and yet if you look at the header of the packets, they have to have a full IP address, and those headers, without thinking about it, could be quite large. And so what's done in LTE and in other systems as well is that the size of that header is compressed. It uses a thing called robust header compression, or ROHC. And that's a key feature of what PDCP does. And then the other thing it does is it handles ciphering. So this is cryptographic ciphering. This is what provides security in the system, and so it deals with doing the ciphering and deciphering in the system. Next layer down is RLC, or radio link control layer, and it's really main task is to take care of automatic retransmission of failed packets. Now, you don't necessarily have to retransmit failed packets. There are different modes. There's a transparent mode, an unacknowledged mode, and an acknowledged mode. Now, if you're in an unacknowledged mode, maybe you don't care whether those packets get through. You don't need to retransmit them. But in acknowledged mode does require that failed packets get retransmitted. And this is different than the ARQ that's going on in the hybrid ARQ protocol down at the lower layer. Hybrid ARQ is very closely connected to the physical layer, and it deals with retransmitting packets immediately upon reception or incorrect reception of a packet. Where RLC is more a higher layer. This is if hybrid ARQ fails, this operates over much longer time scales, and it deals with basically kicking in when hybrid ARQ doesn't work. So how does the RLC ARQ protocol work? Well, it works on the basis of status reports. So status reports are sent periodically from the receiver to a transmitter. What's in the status report? Well, it has a list of the bad packets, or PDUs, and the sequence numbers that is one higher than the last good PDU. And so certain events can trigger a status report. Whenever the receiver detects a bad packet or PDU, it'll trigger a status report, or upon polling. So the transmitter could send a poll and say, hey, have you received everything? And then the receiver will reply back with a status report. So there's some conditions that can lead to a poll. Basically, if it's been a while, so more than a certain number of packets or PDUs, or a certain number of bytes, or if the transmission buffer is empty, or upon a timer or a window stalling, or a timer expiring. So there's various things that can cause a poll to be sent, and then if either a poll is sent or if a bad RLC PDU is detected, then the receiver will respond with a status report, and status report will then let the transmitter know what needs to be resent. Now, one issue with the retransmission protocol is you are going over wireless, and we talked earlier about how through scheduling the bandwidth could vary. So you transmit one packet and maybe the size is 600, but then suppose you need to retransmit that and you no longer have available to you a bandwidth that'll support this size 600 message. So you might actually need to send it over two messages, maybe one of size 200 and one over size 400. So RLC protocol will handle this idea of resegmenting, so taking this larger packet, and when you need to retransmit it, maybe retransmitting it as two smaller packets. So that's all I had for this fairly short lecture, and thank you for joining me, and I look forward to you joining me on the next lecture. Thank you.